Take a look at this interesting geometry problem. It's from the 2022 AIME 1, and it's problem number 11. So, let ABCD be a parallelogram with angle BAD, which is this angle, is less than 90 degrees. A circle is tangent to sides DA, AB, and BC, and intersects diagonal AC at points P and Q with AP less than AQ as shown. Suppose, here's the interesting part, that AP is 3, PQ is 9, and QC is 16. Then we want to find the area of ABCD, which is going to be in this form, and we just want to find the sum of that. So we'll worry about that once we get there. But for now, we're trying to find the area of ABCD. The first thing when you look at this is you link of power of the point. So the power of the point basically has that this AQ, and for good measure, I'm going to call this point right here M, this point right here N, where it's exactly tangent. And so AM is tangent to the circle, and AQ is also a secant through the circle. So what we have here is that AP, or I'll just write the numbers. We have that 3 times 3 plus 9 is equal to AM squared. And so 3 times 3 plus 9, that's 36, equals AM squared. So AM equals 6. This is 6. And we can do the exact same thing on this side to find CN. So we get 9, or not 9, it's going to be 16 times 16 plus 9. 16 times 16 plus 9 equals CN squared. So you get 16 times 25 equals CN squared. CN equals 4 times 5 equals 20. So this is 20. So now we have two lengths, and we also know that these are tangent exactly. So these are going to be right angles, and the midpoint of this is going to be exactly the midpoint of the circle. So what else can we find? Let's draw in this line, which is going to be, it's also the radius to the tangent BA. And what this gives us is something very interesting, because we know this is 6, so this is also a line that's also tangent. Because both of them are emanating from the same point, they both have the same side length. So this is 6, this is 6. And similarly, we have some BN here. I'm going to call it like A, or maybe I'll call it X, just so we don't get confused with the 9. So I'll call this X. We know that this is also going to be X, and I'll just call this point K for good measure. So we have that this is X, this is X, this is 6, this is 6. But again, we're still stuck with trying to find out stuff. And so the next thing that I did was, well, if this is 6, this is X, let's try extending this to form a right triangle, and maybe we can do something with a right triangle. So consider this right triangle. Let's call this like point, I'm running out of points, so let's just call this point E. So we have that this BE here is going to be 6 minus X, because this ENMA, or AMNE, this is a rectangle, so this EB is 6 minus X. And we can basically find EA, and EA is really important because this is the height of the parallelogram. That's one step closer to finding the area, because the area is just the height times this base. So let's try to find the height. And it's not going to be perfect, but the height is, so let's say EA squared is going to equal 6 plus x squared minus 6 minus x squared, which is going to equal, the 6 squared and the 6 squared are going to cancel, the x squared and the x squared are going to cancel, so we're going to be left with 12x minus negative 12x equals 24x. So EA is going to equal square root of 24x, which is going to be 2 square root of 6x, which x is also inside the square root, so that's important. So this is 2 square root 6x. So that's one thing, but let's see if you can try to find something else. And, we have one right triangle here. Why don't we consider this bigger right triangle, triangle ACE? Looking at Pythagorean Theorem on triangle ACE, we get that EA squared plus this gigantic EC, which is 6 minus x plus x, that's just 6, plus 20, 26 squared is going to equal 3 plus 9 plus 16, and 9 plus 16 is 25, 25 plus 3 is 28, so this is going to equal 28 squared. And we also know what EA squared is, that's just 24x, so we get that 24x equals 28 squared minus 26 squared, and so now we have an explicit expression where we can solve for x. So let's just go through it. 24x, and I'm just going to use difference of squares here, which is going to be 2 times 54. And so 12x is going to equal 54. X is going to equal, when we divide both sides by 6, we're going to get, 2x is going to equal 9. X equals 9 halves. So that's a really important result, is that x equals 9 halves. So we know that this is right here is 9 halves. So the area, or the side length of this entire base here, BC, we know that BC equals BN plus NC, which is equal to 9 halves plus 20, which is equal to, I'm just going to convert this to 40 halves, 49 over 2. So that's this side length, and since we also have x, we also know EA. EA is equal to, what is it? 2 times the square root of 6x, which is equal to 2 times square root of 6 times 9 halves. This becomes 27 under here. So it's 2 square root 27, which equals 6 times the square root of 3. So we found EA. We have the base here, BC. So the area is EA times BC, which is equal to 6 times the square root of 3 times 49 over 2. Once we simplify this, we get 3 times 49 times the square root of 3. 3 times 49 is 120. That's 27. So 147 square root 3. That's the area of ABCD. And as we can see, I'm just going to write it back up here. M square root n, it's exactly 147 square root 3. And so we want to find what m plus n is. Well, we can confirm that this is in the form of this, so we're doing something right. And so if we find that m plus n, that's just 147 plus 3 equals 150, which is the answer to this really cool geometry problem. Thanks for watching, guys.